Hello students, I am Shashank Joshi from Deccan Education Society's Fergusson College, Pune. I am teaching Vocational Electronics. Topic of today's discussion is Operational Amplifier. Operational Amplifier is very versatile circuit and it has several applications in industries as well as in our laboratory. So we construct many circuits using Operational Amplifier. It is necessary to understand details of Operational Amplifier before we construct any circuit of op-amp. So we have to consider all the details. So let us move to presentation. Contents of the chapter. Drawbacks of RC coupled and direct coupled amplifier. Differential amplifier. Need of dual power supply in differential amplifier. Operational amplifier and its requirement. Block diagram of operational amplifier. Operational amplifier parameters. Concept of virtual ground. Linear and non-linear applications of operational amplifier. Linear applications. Inverting amplifier. Non-inverting amplifier. Buffer amplifier. Op-amp adder circuit. Op-amp subtractor circuit. Op-amp integrator circuit. Op-amp differentiator circuit. Op-amp comparator circuit. Op-amp Schmidt trigger circuit. The reference book for this chapter is Electronic Principles by Albert Malvino. Amplifier. Amplifier is an electronic circuit that increases the voltage, current or power of a signal applied at its input. This increment in the signal is represented by gain of an amplifier. Single stage amplifier is a basic circuit used to increase signal level. In various applications, we need high gain amplifiers. The gain of an amplifier is decided by the circuit components and their parameters. If we wish to increase the gain of a single stage amplifier to a high value due to components used in the circuit, the gain has limitations. For many applications, the performance obtained by a single stage amplifier is insufficient, and so several stages are combined to form a multi-stage amplifier. These stages are coupled or connected in cascade. That is, output of first stage is connected to input of second stage and so on. The gain of multi-stage amplifier is a product of gain values of all stages. Operational amplifier has very high gain and single stage amplifier is not sufficient for it. So we have to use cascaded amplifier. There are various coupling methods used in cascaded amplifiers. Based on the methods used for cascading stages, different types of multi-stage amplifiers are available in electronics, namely RC coupled amplifier, transformer coupled amplifier, and direct coupled amplifier. There are drawbacks in RC coupled amplifiers and direct coupled amplifiers. Considering those drawbacks, differential amplifier is used in operational amplifier. RC coupled amplifier. RC coupled amplifiers are the multi-stage amplifiers in which resistance R and capacitor C are used to couple the stages. Figure shows RC coupled amplifier. The gain of RC coupled amplifier decreases at low and high frequencies. That is, very low and high frequencies cannot be amplified using this circuit. Since capacitor is used at the input as well as in the coupling circuit, DC signal cannot be amplified using this circuit. These are the drawbacks in RC coupled amplifier, and so decided to use direct coupled amplifier. Direct coupled amplifier. The multi-stage amplifier circuit in which output of first stage is directly connected to input of second stage is called direct coupled amplifier. Figure shows direct coupled amplifier. We know that transistor parameters like VBE and beta varies with temperature, and so the output of amplifier changes with no relation to input, which is called drift. The output of DC amplifier contains DC component along with amplified AC signal, which is undesirable. This is called DC shift. As the gain is high, any noise signal present at the input of amplifier gets amplified and the output contains noise. Due to these drawbacks, DC amplifiers are also not used in op-amp. These drawbacks are removed in differential amplifier. Differential amplifier. Figure shows differential amplifier. In this, there are transistors and resistors connected and dual power supply is applied to it. Differential amplifier has two identical transistors connected in CE configuration. Emitters of two transistors are in common and resistor is connected to it. Dual power supply is connected to the circuit as shown. Input voltages are applied to bases of transistors. The output of differential amplifier is the voltage between two collectors of transistors. Differential amplifier amplifies the difference between two inputs. When input voltage Vin1 is applied to the base of transistor Q1, the voltage at collector of Q1 is A into Vin1, where A is amplification factor of Q1. Similarly, voltage at collector of transistor Q2 is A into Vin2. As the output of differential amplifier is the voltage between two collectors, we have Vout is equal to A into Vin1 minus A into Vin2. That is A into Vin1 minus Vin2. Thus, the output of differential amplifier is the amplified difference of two inputs applied to amplifier. Differential amplifier has two input terminals. Normally, the output of differential amplifier is the voltage between two collectors, and so the output is differential output. Figure shows dual input differential output amplifier, that is, amplifier having two input terminals and two output terminals. This configuration is also called dual input balanced output differential amplifier. In some applications, differential amplifier is used in another mode, where input signal is applied at two input terminals and output is taken from one terminal. The output is taken from one of the collectors of the transistors used in differential amplifier as shown. This configuration is called differential input single-ended output differential amplifier. This is also called dual input unbalanced output differential amplifier. Need of dual power supply. Conventional amplifier works on single power supply, whereas differential amplifier needs dual power supply. If the single power supply is used, then the working of an amplifier changes. Let single power supply is connected to the differential amplifier as shown. That is, positive terminal is connected to combination of collector resistances and the emitter resistance is connected to ground. When the signal input is applied to Vin1, at that time transistor Q1 starts conducting and current flows through circuit as shown. When this current passes through emitter resistance, voltage is developed across emitter resistance. Due to this emitter voltage, biasing of transistor Q2 changes, that is, operating point, which is Q point of transistor, gets shifted. This gives undesirable output of differential amplifier. As we don't want this, we use dual power supply. When dual power supply is connected to differential amplifier, that is, plus VCC is applied to combination of collector resistances and minus VE is applied to emitter resistances, at that time both the transistors are properly biased for amplification and the bases of transistors are brought down to ground potential, that is 0 volt. Under this condition, when the signal voltage is connected between input terminal and ground, there is no change in operating conditions of transistors and the difference in signal is amplified. Secondly, due to dual power supply, complete sine signal can be amplified. As the bases of transistors are at 0 voltage, both the positive and negative output voltage can be observed. Dual power supply allows the output voltage to vary on either side of ground potential. Dual power supply for op-amp. In laboratory, when we construct operational amplifier circuit, it is necessary to apply dual power supply to the circuit. From single power supplies available in the laboratory, we can construct dual power supply. We use two power supplies. Positive terminal of first power supply is considered as plus VCC and negative terminal of second power supply is considered as minus VEE. Negative terminal of first and positive terminal of second are connected in common, which is stated as ground. Figure shows the connection. Operational amplifier. An operational amplifier is called operational amplifier because it is an amplifier with high gain and high input impedance used especially in circuits for performing mathematical operations like addition, subtraction, integration, differentiation, etc. in analog computers. An operational amplifier is a direct coupled high gain voltage amplifier with a differential input and single-ended output. Differential amplifier is a basic building block of an operational amplifier. Block diagram of operational amplifier. Operational amplifier has 4 blocks as shown in figure. There are 2 differential amplifiers and 2 other circuits. Operational amplifier has 4 blocks as shown in figure. Input stage. Differential amplifier is used as a basic block in operational amplifier. In this stage, differential amplifier with 2 input terminals and 2 output terminals is used. The output is taken from collector terminals of transistors. The output of this stage is connected to intermediate state. This stage also uses differential amplifier. The differential amplifier with 2 input terminals and 1 output terminal is used in this circuit. The output of first stage is connected as an input to this stage. The output of differential amplifier is taken from collector of transistor Q2. Level shifter circuit. Differential amplifiers are direct coupled amplifiers. The output of first stage is connected to intermediate stage, and so the output of intermediate stage contains amplified AC signal with DC shift. This DC shift is undesirable. Level shifter circuit is used to reduce this DC shift to 0 volt. The useful AC signal is present at the output of level shifter circuit. Output stage. The AC signal at the output of level shifter circuit is to be amplified. The output stage has push-pull power amplifier circuit. The signal is amplified in this stage and amplified AC signal is available at the output of operational amplifier. Op-amp symbol. In circuits, normally we use op-amp symbol. On left side, symbol is shown. Non-inverting input, inverting input, output, supply and supply terminals are the terminals normally used in circuit. On right side, op-amp pin configuration is shown. Pin number 1 is offset adjust. Pin number 2 is inverting input. Pin number 3 is non-inverting input. Pin number 4 minus V. Pin number 5 offset adjust. Pin number 6 output. Pin number 7 plus V. And pin number 8 is NC, that is not connected anywhere. Inverting and non-inverting inputs of op-amp. Inverting input. The input of op-amp which is out of phase with the output of op-amp, that is, there is a phase difference of 180 degree in input and output, is called inverting input. It is normally shown by negative sign. Non-inverting input. The input of op-amp which is in phase with output of op-amp, that is, there is 0 degree or 360 degree phase difference in input and output, is called non-inverting input. It is shown by positive sign. Op-amp parameters. Input bias current. In op-amp, input bias current IB is the average of biasing currents IB1 and IB2. IB1 and IB2 are the base currents of first differential amplifier transistors. In order For op-amp to operate, its two terminals have to be supplied with DC currents. These are input bias currents. The manufacturer of op-amp normally specifies the average value of these currents as input bias current. Input bias current is IB1 plus IB2 by 2. Input offset current. The difference between the biasing currents IB1 and IB2 of two terminals of op-amp is input offset current, IB1 minus IB2. The typical value of input bias current IB for op-amp that uses bipolar transistors at input stage is 100 nanoampere and offset current is 10 nanoampere. Op-amps that utilize field effect transistor in the input stage has much smaller input bias current and input offset current of the order of few picoampere. Output offset voltage. When both the input terminals of op-amp are connected to ground, the output of op-amp must be 0. But practically, there is small voltage at the output of op-amp. This voltage is called output offset voltage. Input offset voltage. In practical op-amp circuits, due to output offset voltage, the output of circuit is not correct and the output has to be adjusted to 0. For that adjustment, it is necessary to apply voltage at the input of op-amp. The voltage applied to input of op-amp to adjust its output voltage to 0 is called input offset voltage. Open loop gain. The gain of an amplifier without feedback is called open loop gain. For ideal op-amp, open loop gain is infinite. Normally, practical op-amp has gain of about 1 lakh. This gain is unstable and varies with supply voltage, temperature and aging of device. Gain is equal to V out upon V in. Closed loop gain. In practical circuits, gain should be high and stable. This can be achieved by negative feedback. The gain of an amplifier with feedback is called closed loop gain. Closed loop gain ACL is AOL upon 1 plus AOL into beta, where AOL is open loop gain. Common mode gain. The gain of an amplifier with common input or equal inputs, that is, input signal applied to inverting and non-inverting terminal of op-amp is same or equal. Common mode gain is very small as op-amp amplifies difference in inputs. Common mode rejection ratio, CMRR. This is an important characteristic. Common mode rejection ratio is defined as the ratio of differential mode gain to common mode gain. CMRR is equal to AD upon AC, where AD is differential mode gain and AC is common mode gain. CMRR in decibels is given by 20 into log of AD upon AC. It represents ability to reject common mode input signal. For ideal op-amp, CMRR is infinite. Slew rate. Slew rate is defined as the maximum rate at which the output voltage can change. Slew rate is given by dV out upon dt. Slew rate is the specification which needs to be considered for AC applications of op-amp. The unit of slew rate is volts per microsecond. For IC 741, the value of slew rate is 0.5 volts per microsecond. Frequency response. Figure shows frequency response. Here there are two characteristics. One is for open loop and one is for closed loop. Frequency response curve of an operational amplifier shows variation in gain of an amplifier with applied frequency. Cutoff frequency. Cutoff frequency is the frequency at which gain of an amplifier is 70.7% of the maximum gain value. The open loop bandwidth or cutoff frequency of op-amp is very low. F2OL is 10 Hz. That is, when the frequency is greater than 10 Hz, the gain breaks and rolls off with 20 dB. When negative feedback is used in closed loop circuit, the overall bandwidth increases. F2CL is 10 kHz. Greater the negative feedback, higher is the cutoff frequency. F unity. F unity is the frequency at which gain of an amplifier is 1. F2CL is equal to F unity upon AVCL plus 1 for inverting amplifier, and F2CL is equal to F unity upon AVCL for non-inverting amplifier. From this, we can find gain bandwidth product. Here, AVCL is closed loop voltage gain. F unity is equal to AVCL into F2CL. AVCL into F2CL is gain bandwidth product of an amplifier. F unity is equal to 1 MHz from the frequency response curve. Therefore, gain bandwidth product is equal to 1 MHz. Ideal operational amplifier characteristics. Open loop gain is infinite. Input impedance is infinite. Output impedance is 0. Common mode rejection ratio is infinite. Input bias current is 0. Input offset current is 0. Frequency response is from 0 to infinite frequencies. That is, op-amp can amplify signals from DC to very high frequencies. Input offset voltage is 0. Response time is 0. Output offset voltage is 0. Offset null adjustment. Figure shows circuit for offset null adjustment. In an operational amplifier, when both the inputs are connected to ground as shown, it is expected that the output voltage of an op-amp must be 0. Practically, it is observed that there is a voltage at the output of operational amplifier. This voltage is called output offset voltage. Offset null adjustment is used to reduce this output voltage to 0. In this arrangement, 10 kilo ohm potentiometer is used. Fixed terminals of potentiometer are connected to offset adjust terminals of op-amp, that is pin number 1 and 5. The variable terminal of potentiometer is connected to negative voltage -V, that is pin number 4. The potentiometer is then rotated and the output of an op-amp is observed. As the potentiometer is rotated, output offset voltage reduces to 0. Once offset voltage becomes 0, the potentiometer is kept at the same position throughout the experiment. While adjusting output offset voltage to 0, normally closed loop circuit is used. In this circuit, feedback resistor is connected between output and inverting input terminal of operational amplifier. Concept of virtual ground. In operational amplifier, this concept is very important. The entire circuit working is based on this concept of virtual ground. Figure shows an amplifier in which part of output is fed back to input, that is closed loop circuit. We know that gain of an amplifier is V out upon V in. Therefore, A is equal to V out upon V in. Rearranging, we get V in is equal to V out upon A. As it amplifies the difference, V in is V1 minus V2. So V1 minus V2 is equal to V out upon A. We know that for ideal op-amp, gain is infinite. As A is infinite, V out upon A is 0. That is, V1 minus V2 is equal to 0. That gives V1 is equal to V2. That is, voltage at inverting terminal and voltage at non-inverting terminal are equal. As the voltages are equal, the difference between input terminals of op-amp epsilon is 0. Non-inverting terminal is connected to ground, that is at 0 volts, and so inverting terminal is considered to be at 0. Though the voltage at inverting terminal is considered to be 0, it does not sink the current but allows the current to pass through feedback path, that is Even it is at ground potential, it does not have the characteristics of actual ground, and so it is called virtual ground. So friends, in today's lecture, we have seen drawbacks of RC coupled amplifier and direct coupled amplifier. Due to these drawbacks, these amplifiers are not used in operational amplifier, and so differential amplifier is considered. We have seen differential amplifier which uses two transistors and dual power supply is connected to it. Why dual power supply is necessary in this circuit, that also we have seen. After that, we have seen some parameters of operational amplifier such as input bias current, input offset voltage, output offset voltage, frequency response, and few more. In next lecture, we will study various op-amp circuits. Thank you.